Let's say we have a problem like this, where there's a block being pushed forward onto an icy surface at 12.5 meters per second. There's a coefficient of friction between the block and the ice of 0.0785, which tells us that once that block is pushed on, it starts slowing down because friction slows its motion. We've been asked to find how far forward the block travels before coming to rest. So there's a couple of things that we know, the givens. We know that the initial velocity of the block is 12.5. They're basically telling us find the distance that it travels, find how far forward it goes, when the final velocity is 0. And the coefficient of friction is 0.0785. Like that. So a problem like this is best solved with the work kinetic energy theorem. So before we can do too much here, the best thing is to draw a free body diagram. That's how we usually start these things. So let's say here's the block, and of course if it's on a horizontal surface, weight pulls down, and we call the weight the gravitational force now since W is reserved for work. The normal force pushes up, and each of those is equal to mg, and friction pulls back, Fk, and we know that friction is equal to mu times the normal force, which will be mu times mg. Okay then, the work kinetic energy theorem says that the net work, let me try that again, the net work on a block, the net work, W net, on our block here is equal to the change in kinetic energy, which is Ke final minus Ke initial. Alright. So the block, let's remember, is traveling forward some distance, d, which is what we're trying to find. It comes to rest, which means that the final kinetic energy is 0, because the final velocity is 0. In these problems, you always plug in for W net. You always plug in the net force times the distance times the cosine of theta, where theta is the angle between the net force and the distance. And then on the right side, we just have minus the initial Ke, which is this, 1/2 mv squared. And good, we're ready to go. The net force in problems like this, right, Fn and Fg cancel out. We could just cross those out if we wanted. And so the only unbalanced force, the net force, is Fk. So we can plug in Fk here for Fnet. And here's an important thing to remember. When you plug in for Fnet, you always plug in a positive number into this equation because work is a scalar. So even though the net force, which is Fk, even though the net force points to the left, which is the negative direction, you don't put a negative number here. You just plug in the positive value. Right? So that means I'm going to rewrite Fnet as mu mg, because that is what we said the kinetic friction force equals. Then I'm going to have my d here. Cosine of theta. In every problem where the net force is the friction force, you will always have the angle of 180 degrees, because friction always points in the opposite direction as the distance traveled. You see this here in the picture we've drawn. The distance is forward, the block's moving forward, and of course friction goes in the opposite direction always. So the block is being pulled by friction to the left, whereas it's moving to the right. So this is a 180 degree angle, right? The angular separation between these two arrowheads is 180. Good, so you have to plug in cosine of 180, which is -1. And over here, we have 1/2 mv squared. And look at this, the beauty in these problems is that the masses cancel. So you don't need to know what the mass of the block is in order to solve for how far forward it goes. Which is interesting, because if you were to take a giant block and slide it forward at the same speed as you took a small hockey puck, as long as there was the same kinetic friction coefficient, as long as this coefficient was the same, the two things would travel the same distance. The amount of mass that the object has doesn't affect how far forward it goes. Kind of interesting fact. That would be a good multiple choice question on a test, don't you think? Okay, so mu, we can plug in. We know that value, 0.0785. G is 9.81. D is what we're finding. And of course, look at this. The negative here cancels with this negative. And on the right, we have 1/2. The mass canceled. And the initial velocity squared, VI was 12.5. So you can solve for the distance here. You have to divide the left and right sides by 0.0785 and by 9.81. And when you do that, what do you get? You get 101.44984, and with sig figs we round that to 101. Wow, that is pretty far forward. So that's our answer, and that's how you solve problems involving the work done by friction, which is what the heading here says. These are important problems because the work done by friction starts to appear in other more complicated problems. So it's really good to have this kind of problem just right there under your belt. You can immediately see how to solve this type of scenario. Good work.